Hi, everyone. Welcome and thank you for joining us this evening. Some of you may know me already. My name is Juhayn Al-Ghafri, and I am the Communications and Membership Coordinator at ESO. And today we have Dr. Petr Vahalík, who's currently working as an assistant professor and researcher at Mendel University in Brno. Czech Republic. And his research scope and specialization are in the implementation of geographic information system and remote sensing in landscape engineering, forestry, and management of natural resources. So today he will give us a brief summary of modern trends in geotechnologies. And I would just like to remind everyone to please keep your microphone on mute and camera off so we can ensure the best quality of connection. And we will also open the floor to questions at the end of the lecture. Dr. Petr, you can start.
Hello, good afternoon. For those who knows me, nice to meet you again. For those who never met me yet, it's a pleasure to meet you. Thank you for words. Thank you for your time. I will try to be brief. So very briefly, we will go through modern tools of geotechnology and its use in environmental research. Thank you for a short introduction of me. I will continue with it a little bit, and I would like to introduce my research and my activities, my research activities, just to let you know me better. So I'm involved in many projects. In this slide, you can see not complete list of projects I'm dealing with nowadays. So I'm active in global monitoring of quarantine species in forest pathology. I do cooperate with forest pathologists in the project of global spreading of few quarantine species, Dotistroma species, Fusarium circinatum, and Phytophthora species. Also, I'm active in Georgia, where I help to establish Georgian forestry forest management, mainly in Caucasus range. I am also active in Yemen, specifically in Socotra archipelago, where we do development of Socotra archipelago in general, and also we as a team do scientific research of this specific place. Also, I'm active in Ethiopia and in Zambia. In Ethiopia and in Zambia, I do cooperate in the process of land management and improvement of land management to support local farmers and also to support local environmental research. Well, I mentioned it's not a complete list, and the list is quite longer. Also, I'm active in Oman. Exactly during last year, I was part. I do cooperated with ESO in the process of modeling and mapping of Bosphorus Sacra in the Far Mountains. So, well, I'm active worldwide, and in all those projects, my duty are geotechnologies. So that is why we are going to talk about geotechnologies, and I will show you some examples, what technology we are using nowadays, what is effective in our research, and I hope that I will show you some technology which can be quite new for you, and I believe it can be quite useful for you and your research. So the whole presentation will be structured into three parts. The first part will be about field data collection, how we are using web mapping servers in the field to collect the data. The second part is going to be about remote sensing on a local level, how we are using UAVs and drones in the field to collect data. And the third part will be remote sensing on local, regional, or national level. How are we using satellite imagery and how we do data analysis of satellite imagery to get information on a local, regional, or national level. So this is the structure of my presentation, and let's start with it. Before we start, sorry, I'm a researcher and also teacher, and some of you are specialists in geotechnology, some of you are not. So very, very briefly, before we start with those three mentioned parts, what is geotechnology? Geotechnology is a very useful tool. It consists of three parts: GPS, GIS, and RS, Global Positioning System, Geographic Information System, and Remote Sensing. GPS, you all know GPS. It's a tool providing a location of the data. Remote sensing is a tool providing the data. And GIS, Geographic Information System, is a tool to process it all together to produce maps or models. Those maps or models can be historical, actual, and also it can be predictive. And this is very important part of geotechnology. I'm not telling you that we can see the future, but I'm telling you that we can analyze the effect of our activity before we start with such activity. And this is very important. So those predictive models and maps are very, very useful, especially in environmental research or in environmental activities. So this is in general, what is geotechnology about? Now, how it works in a process of environmental research or environmental activities. This slide looks quite complex, but I think it's understandable. It starts on the left side with field data measurement, with remote sensing, simply with the data. The data goes to the right side to GIS, the tool which can process it all. An output of GIS is information, tools, analysis, visualization, whatever. Simply, in general, it's decision support system. And decision support system is a way how to provide information to those people who are in charge, to local authorities and other who make decisions, because you cannot make good decisions without the knowledge, and you cannot have knowledge without good and proper and accurate information. And this is how decision support system works. We provide informations to make good decisions. So in very, very general way, this is what is geotechnology in environmental research about. And let's go to our three parts. Let's go to the field first. What technology we are using in the field nowadays? From my point of view, the most effective way how to collect the data in the field is using web mapping servers connected with mobile apps. Because this technology is very available, and I mentioned it's very effective. How it works? Using cloud of, and literally we are using a cloud of ArcGIS online platform. We create a web mapping server. This web mapping server is structured by variable layers, variable data layers, and those data layers are predefined to obtain necessary attributes. Simply, what kind of information, what kind of data you want to collect in a field. Those layers and those attributes are predefined, and that is why in a field, in your form, you can see your position, you can choose from variable layers, which is useful for you in the field. And when you want to collect the data, you can simply click on plus button, and you can fill predefined attributes. You can use pop-roll menu, choose the answers, and very effectively and very fast collect the data. The whole system works also offline. If you're offline in the field, you can collect the data. That your data is in your phone. When you're back home in the couch, you can click on synchronize, and all the data are going to the server. And also, all the data from the server, like the data from other data collectors, are going to your phone. Simply, all the data of all the users of the same system are mutually shared. And that is why the system is very effective in the field. It's very fast, it's very comfortable, and we proved that it works because this is the system which we use in practically all our projects. So I mentioned we are using platform of ArcGIS Online. This is the platform where we create the whole system. In the phone, we are using mobile application ArcGIS Field Maps. It's a brand new application, which is quite fine. It works fast, and there is a lot of tools which you can use directly in the field. And the question of accuracy of the data, accuracy strongly relates to accuracy of your phone, accuracy of position of your phone. And such accuracy of your phone can be between, let's say, 5 and 10 meters. It depends on the terrain, it depends on constellation of satellites, it depends on manufacturers. If such accuracy of, let's say, plus minus 5 to 10 meters is not enough for you, such accuracy can be enhanced using so-called RTK network. RTK means real-time kinematics. your phone can be connected with external antenna, and this external antenna is connected with a satellite RTK system. I have to mention the system is paid system. You have to pay for such a system, but with such a RTK, you can enhance accuracy, positional accuracy of your phone into, let's say, tens of centimeters. And such accuracy is perfectly fine for any kind of data collection from point of view of environmental research, like to do inventory of trees, inventory of plants, whatever you need to record in the field itself. So this is just a structure of the system which we are using in the field. Let's see some outputs, because all those technology I would like to describe to you based on real outputs we have. So I've got two web mapping servers right here. I can run it. Well, I hope now you can see web mapping server, right? And where are we? We are in Zambia, somewhere in the south part of Zambia. And this project is about land management. So how we use this technology in the field, not just we, but also people who participated with us, people who cooperate with us, local authorities and many others. So it was necessary to collect in our area of interest, it was necessary to collect point vector layer of all farms, because this project should support the farms and their farming to enhance their crops and whatever. So those red points are the farms. When you click on a point, you can see that this farm is property of Mr. Sichaza Murazababa Betty. Sorry, it's not a man, it's a lady. And you can see some attributes about this farm. There is a lot of information about every single farm. We've got also sources of water. Those blue points are sources of water, so you can click on a point and you can see some attributes related to the source of the water. Those data are very crucial for all the people who do planning of those farms, because they do planning of where to transport products, how to process the products, how to change land management and whatever. But this basis is very important, like source of information for those people who are in charge, who do decisions, who do planning of this farming system. There is much more layers. For example, this moisture differences. This moisture differences layer is based on satellite imagery, and simply it informed how the landscape can penetrate water. It's a difference between content of water in the soil and plant bodies between the end of wet season and dry season, rainy season and dry season. So when I zoom somewhere here, you can see that there are some fields. On the left side, you can see blue and green fields, and on the right side, you can see red and yellow fields. Blue color means that there is no significant change in content of humidity in soil or in plants and trees. It means that those blue fields have a good management because it can keep its water. And compared to those blue fields, there are red fields. The management is not well managed because those fields are not able to hold its water. So we can inform local authorities where the management is okay, where the management is not okay, and then not just authorities, but specialists in agronomy, they're going to the field and they do the research. So what is happening here and what is not happening here, and how to improve it. So this is just one of many informations which we can provide to make good decisions. Let's jump to another web mapping server. Maybe it's more close to Oman because we are going to Socotra Island, which is located in Arabic Sea, about 500, 600 kilometers south from Salalah. And on Socotra Island is the homeland of all Boswellia trees, because there is 11 species of Boswellia trees. And during last 3 years, we were dealing, and we still continue with the project of protection of all those Boswellia trees. So I can turn on list of layers of those trees, and you can see 11 species of Boswellia trees. When you click on a point, you can get information about the tree, who collected the data, and so on. So there is quite a lot of information in this database: who collected the data, pictures, whatever date when it was collected. Well, it's quite complex database, and a lot of people worked to create such a data layer. It took more than 2 years to finish this research, and the research is still active. We still work there. Why we collected such data? Because no one ever recorded or mapped the population of all 11 species. Such data is necessary to have to evaluate threat of all those Boswellia tree species. So we used methodology of IUCN evaluation to say which species is more endangered than others. That's just one output of this study. Another output is that we do analyze environmental needs of every single species. And nowadays we are using such database to spatially analyze which parts of the island are able to provide environmental needs to which specific Boswellia species. It means the output will be the map which inform everyone about if you want to regenerate or plant tree seedlings somewhere, where to plant a specific species to follow environmental needs of all those species. So that's another research we are dealing with. And this is, I think, quite nice example of how we used web mapping servers to collect such amount of data. Altogether, we recorded more than 13,000 trees, individual trees. We did not record the trees only using web mapping servers, also in some localities which are not accessible, like steep cliffs or hard accessible areas. There we use drones to fly such areas to map those trees. I think with the drone, we mapped about 5,000 trees from all 13,000 trees recorded till now. This is just another example how to use web mapping servers in the field to fast and effectively collect data. Let's go back to our presentation. So in this slide, you can see also one output from research in Oman, which we did together with the ESO, where I was glad to cooperate. And you can see population structure of frankincense type in Dhofar Mountains. So you can see in which area there is Hojari, Nejdi, Shazri, and Shabi type of frankincense or type of Boswellia sacra species. On the left side, there is just a picture I wanted to mention. You can see this big stone and this very small Boswellia tree. This big stone is located on Samha Island. It's a very tiny, small island located to the southwest from Socotra Island. And on Samha Islands, there is, in 2010, there was discovered a new species of Boswellia called the Boswellia samhaensis. This Boswellia samhaensis is a very dwarf tree. It's a very tiny, small tree, just a few decimeters height tree. And no one ever mapped the population of this Boswellia samhaensis. That is why we did it last year. And on this stone, it is located more than 2/3 of the world population of the whole Boswellia samhaensis species. So it's a big stone. And at the top of the stone, there is more than 2/3 of the whole population. Nearby this stone, there's more stones with some trees on the top of it. So that's quite, from environmental point of view, it's very important, interesting. Of course, location of the stone is quite secret because there is a lot of people who wants to collect seedlings, seeds, and such a fragile population is very endangered. It's just a unique population of Boswellia samhaensis trees. Okay, enough of web mapping servers. In general, it's very effective, it's very useful, and it works. It's proved by all our activities, and we still continue with this approach to collect the field data. Let's jump to the second part, how we use UAVs and or drones or copters or wings if you want, how we use such technology to collect data in a field. Well, we can separate UAVs into three categories: small and cheap, bigger and more expensive, advanced and very expensive. The difference is mainly in price, and also the differences are in ability of copter or wing to carry more sophisticated sensors, and of course to carry more, let's say, heavier sensors. What can you do with those small and cheap commercial copters? Well, you can create a very detailed orthophoto image, and also you can create digital surface model. It's very useful output, and we use it very commonly. With bigger and more expensive copters or wings, you can use more sophisticated sensors, like to create near-infrared images or thermal images. Or nowadays, we are working with a hexacopter, which is able to carry a LiDAR sensor, so we can do LiDAR scanning using a copter. But the main difference is the price. Those more sophisticated copters are much more expensive than those cheap copters, and that is why I truly prefer those small and cheap copters. Why? Simply because it's easy to destroy a UAV, and it's always better to destroy UAV with the price of $300 than $3,000 or $30,000. So, and also I have to mention, it's easier to travel with those small and cheap UAVs, because with those bigger drones, it's administratively, it's very complicated to travel and to do any type of research abroad. That's just in general how we can separate UAVs. Let's see some outputs, how we used UAVs, some examples. So I've got three examples for you. The first example in the upper part of the slide, it's example from Socotra Island again. So on this picture, you can see Fermihin area. It's right in the middle of the island, and it's the last true dragon blood forest on Earth. All other localities with let's say quantity of dragon trees are not forests. Those localities are woodlands. But Fermihin is truly, according to terms of FAO, it's the last true forest of dragon blood trees on Earth. And no one did complex or complete inventarization process of this locality, because it's quite a huge locality, let's say about 700 hectares. And estimation was that there is between 20,000 and 80,000 dragon blood trees. So we decided to make inventory of this unique locality, and that is why we used the small drones. We used two tandem of them, so two drones. It took 3 days of flights, and after 3 days and let's say 1 week of data processing, we created complex inventory. You can see it on a picture in this right upper corner. So we did a full inventory of the whole Fermihin forest. So we know position of every single crown of every single tree, and because we know also the size of the crown, we can extrapolate the age structure of the whole forest. Together with the living trees, so we did inventorization of all the dead trees, lying tree bodies, and with analysis of those lying tree bodies, we identified which cyclone killed those trees. So also with this dead trees inventory, we can understand this locality much more, and nowadays we understand much more how to protect this very unique part of the island. This is just an example of how to use UAVs in forest inventory on a sample of dragon blood trees in Fermihin area. Another example in the middle, you can see we are back in Zambia, and in Zambia, when our specialists in agronomy wants to establish, let's say, silvopastoral system in some specific area, in some specific farm, what they need at the beginning is very detailed orthophoto image. Well, orthophoto image from Google Maps, it's quite okay, but spatial accuracy of Google Map orthophoto is not enough. Spatial accuracy of Google orthophoto is about 30 centimeters per pixel. with a small cheap drone, I can create orthophoto image with spatial resolution of 3 centimeters. It means 10 times more detailed. And mainly from Google orthophoto image, you cannot guarantee when it was recorded. Maybe it was last year, maybe it was 5 years ago. If you need actual data, UAV is best to get it, because you have actual data with very high spatial resolution. And all this, all those data, the whole orthophoto image is located in coordinates. It means that those specialists who design next activities, they can use such a background to draw what seedlings are going to be seeded wherever, where to manipulate water. Simply, they can design whatever they need to. And everything what they design, I can transfer back to web mapping server, and people in the field, they can use the phone to know exactly where to do plantings, where to manage water, simply what to do in a field. So this is how we can combine UAV data with web mapping servers. The third example at the bottom of this slide is another example from Zambia, how we can use digital surface models in land management. This is example of reconstruction of the small water dam. This water dam doesn't collect any water anymore because the dam itself is destroyed and it's all full of sediments. And the task to me was to use a drone to evaluate and calculate how much stones, what is amount of stones and concrete to necessarily use to build a dam, and also how what is amount of soil or sediments we need to move out from this dam. Because with such a calculation, well, I used UAV, I created a digital surface model, and with this digital surface model, I can truly accurately calculate all those dimensions. And because we know dimensions, how much soil we need to remove, how much stones and concrete we need to bring, then we can calculate what will be the total price of the whole action. And this is very important information in the whole process of realization. This is just another example of how we can use UAVs. All those outputs are created using DJI Mavic Mini. The price of such a small, let's say, toy. The price of such a toy is about $300. So we don't need very expensive drones to get perfect outputs. You can get perfect outputs even with a cheap, let's call them toy UAVs. Okay, enough of drones, and let's jump to the Earth orbit, and let's talk a little bit about satellites, because I see that the time is running. So the last part will be about satellites. What satellite imagery, what satellite constellation we are using in our research? There's more than 2,000 still operational satellites on the Earth orbit, so it's a very busy place. Don't worry, I'm not going to talk about 2,000 types of satellites. Of course, no. I'm going to talk about how to choose a satellite constellation for your purposes. When you think about what kind of satellites you want to use or you need to use, you have to think in 4 different parameters, about 4 different parameters. It's 4 different resolutions: spectral, spatial, radiometric, and temporal. Spectral resolution, it means what parts of electromagnetic spectrum can be recorded by satellite. Spatial resolution, it's a detail, size of the pixel. Radiometric resolution, it's intensity of electromagnetic electromagnetic radiation. Simply what smallest part of electromagnetic spectrum you can collect or satellite can record. And the last resolution, temporal resolution, how often you can get the data about the same part of the Earth's surface. So those are 4 types of resolution you have to think about. And the last aspect you have to think about to choose proper satellite constellation is a price, of course, because there are commercial satellites which produce really nice outputs, but those outputs are quite expensive. I prefer, and I think most of you prefer, to use outputs which are for free. So let's see just 3 examples of freely available satellite constellations which you can use nowadays. The first one is Landsat. Second one are Sentinels as output of Copernicus mission, and the last one are PlanetScopes. The first one, Landsat, Landsat 1 was launched to the Earth orbit in early 70s, in 1972. So with Landsat collection, you can go deep to the history. You can go 50 years to the history, but you have to see what happened on the Earth's surface globally. But you have to remember that more deep to the history you go, less detail you can get because of the technology development. So in 70s, you can have spatial resolution of 100 meters. Nowadays with Landsat 8, you can have spatial resolution between 10 and 30 meters. Landsat was continuously replaced by Copernicus project. Copernicus project, I think you all mentioned, you all know the name of the project because it's well known, and scientifically it's one of the most challenging projects nowadays. The main idea of Copernicus project is that all the people on planet should have right to see what is happening with environment, and that is why all the products of Copernicus project is freely available to all of you. The outputs of Copernicus project are constellations of satellites called Sentinels. Those Sentinels are radar satellites or multispectral satellites. Nowadays there is 1, 2, 3, 4, 5. There is 6 Sentinels already on the Earth orbits, and more Sentinels are coming. Well, those data are very, very useful and very, very effective in the process of monitoring of environment, because those satellites are specifically designed for environmental monitoring or monitoring of environment. Okay, those are Sentinels. The last example I put on a slide is PlanetScopes. Planet is an American commercial company. Commercial means that they are not offering data for free, but in 2020 they changed their strategy, and since 2020, if you want to use their data for non-commercial use, you can use it for free with the limit of 5,000 square kilometers per month. So for non-commercial use, scientific use, you can use PlanetScopes for free with the limit of 5,000 square kilometers per month. What is the difference between Sentinels and PlanetScopes? The differences are in spatial resolution. All Sentinels have spatial resolution of 10 meters. PlanetScopes have spatial resolution of 3.5 meters. It means they are 3 times more detailed, and it's quite nice. Right here on this slide, you can see just how to compare, or you can see differences between Sentinel on the right side. It's a Sentinel-2 on the right side, and PlanetScope on the left side. So you can see those images in true colors, and also you can see NDVI models. It means intensity of photosynthesis. So with Sentinels, you can easily monitor, let's say, forest stands or fields. With PlanetScopes, you can recognize specific trees, so it's much more detailed. But also it's necessary to consider as a fact that with more detailed data, one image is covering smaller area. So if you want to cover a larger area with satellite data, then it's more beneficial to use Sentinel-2. If you are more interested in a detail in a smaller area, then choose PlanetScopes. And I promise you in very general way. So let's continue. Another output of a Copernicus mission is EO Browser. And EO Browser is a fantastic tool. EO Browser is a library of satellite images. There is plenty of libraries, online places where to get satellite data. And every single library primarily serves as a source of the satellite images. But EO Browser is different, because I mentioned what is the main idea of Copernicus project. They are trying to bring satellite imagery to the users. And thanks to EO Browser, nowadays, you don't need to be specialist in remote sensing to do basic analysis of satellite data. And nowadays, you don't need to even download the satellite data, because all images from Sentinel constellation are going to the servers, and those servers continuously process the basic processing of those images. And using your browser, you as a user, you can get the output. It means you don't need to analyze it anymore. What outputs you can get? You can get radiometric indices. It means health status of vegetation, humidity indices, orthophoto images in true colors. You can get time lapses. It means wherever in the world you can make a time lapse what happened in that area, but only using Sentinel satellites. It means you can go back into 2015. So nowadays it's 7 years. So last 7 years you can analyze whatever, wherever in the world for free, and you don't need to be a specialist. You don't need to download the data, and I think it's fantastic. I hope that all of you today evening you will play a lot of games with your browser. It's for free. You can just go through simple registration, and you can try how it works. There are really nice tutorials, and it's very user-friendly interface. So you will see that you can have really nice and let's say specific outputs, even if you are not specialists. So what outputs you can have from your browser? This is on this slide. You can see what you can get from your browser. This is just an example of a humidity index, let's call it a moisture index, in some polygon somewhere, wherever in the world. And you can get the graph, how the humidity or moisture was recorded during the last 5 years. So you can see dry season, wet seasons, and when it happened. If in some area there was some extreme rainy even, it's all recorded, and you can check what happened there. Also with your browsers, you can make time lapses. So in this slide, you can see it's upper part of Zambezi river next to the city of Mongu, and you can see floods of Zambezi river, and now you can see how the dry season is coming. Now you can see crops, and after crops, flood season again, and the dry season is coming, and now we can see the crops. And such a time lapse you can get in just a few minutes. So it's very easy to get a time lapse about some specific area of your interest, and you can get truly valuable information about what is happening in this area and how to deal with it. This is just an example of how to use it. Another example, I mentioned a humidity difference. So you can analyze the humidity difference between dry and wet season, and identify in which parts, in which fields there is some kind of problem, and in which fields or which fields are not suffering with droughts and whatever. When you combine such output with a map of biotopes, then you can have complex, let's say, spatial evaluation of the situation in some specific areas. So in this slide, you can see it's again in Zambia. So you can see woodlands, wetlands, lakes, and agricultural land, which is separated into 4 categories like stable humidity, droughts, intense droughts, and very intense droughts. It's again, it's very important information for land management planning in general. And well, time is running. The last output I would like to show you is how to use satellite imagery for monitoring in general. Well, this is an example from Ethiopia, where we have multiple projects, and this specific project is a nearby lake of Avasa in the middle of Ethiopia, and there are some fields where the management were changed, and they still continuously use different land management to enhance the vitality of crops, to enhance humidity of the soil, and so on and so on. And such an effect should be visible with effect of vegetation activity or health status of the vegetation inside those plots. And this is what how I do monitoring of those localities. So using NDVI indice, vegetation indice, I analyzed the indice before the intervention started, after the intervention ended. And in this table, you can see just a comparison between amount or average of NDVI of the whole of the specific plot. And in the last field, you can see a percent ratio that activity of vegetation in some specific plot enhanced about between 10 and 20%. In case that, and of course, I can still continue with such a monitoring. Every year, I can analyze and compare if the vegetation activity in those plots is growing or not. But of course, it can be temporarily affected by climate, by weather, because it happened this year, that this year in Ethiopia was extremely dry. And that is why when I analyzed NDVI differences between between now and 1 year ago, activity of vegetation decreased a little bit. In general, in average, about 5%. But it doesn't necessarily mean that local people doesn't manage soil or their fields in a wrong way, but it means that it was dry, and it's proved by the last picture on this slide. And you can see graph of humidity index in 2022 and 2021 and 22, and you can see that the wet season in 2021 was almost, let's say, for 25% longer than in 2022. Simply 2022 was drier. That is why vegetation activity is decreased a little bit, but it didn't decrease under the level when we started with those interventions. So it still works, just the climate affected, let's say, activity of vegetation. So this is just another example how we can use satellite imagery for continuous monitoring of our actions. If something is wrong or if it works and what is happening somewhere. And to do such monitoring, I don't need to leave my office. I can do it all from here. Of course, every single action in a field should be supported with the local people, because you can never manage everything from your office, but you can get quite valuable information and data from satellite imagery. Sorry, I'm talking more than 30 minutes now. So let's do some summary. So on a local level, we are using web mapping servers and we are using UAVs because such a technology provides very accurate data and very useful data, and it's very available to all of you nowadays. On a local level, or let's say a remote level, we are using satellite imagery. We are trying to use as much freely available satellite imagery as possible, because nowadays there are freely available satellite data which can be used in monitoring of environment or whatever you need to, and such data is for free. And also with the new tools like your browser, you don't need to be specialists anymore, and you can use such a technology and you can get very important informations to get knowledge to make good decisions. So thank you very much for your attention, and I'll be happy to answer all your questions. And sorry